Good morning, everyone. Today we have our guest. Her name is Dr. SP Engineering Ma'am. She is an assistant professor in selection grade biomedical engineering department in the School of Bioengineering in SRB University. Overall, she has a 19 years of teaching experience in biomedical instrumentation field. She has done MTech from the biomedical engineering from May 2005 from IIT. She has overall published 28 research articles in reputed journals and attended more than 21 conferences. And overall, she has 3 patents, completed 5 online courses too. Now it's over to Angeline Ma'am. She will be having a lecture on medical image analysis. Ma'am, you can over to you.
Okay, thank you, Anupam, for your introduction. Whether my voice is audible?
Audible, ma'am.
Yes. Good morning to all present here. So, I would like to concentrate the topic feature extraction technique in medical imaging analysis because most of them are not giving much importance to this particular point. Uh, Hope you all remember if we are developing some computer aided diagnosis system, if you see the architecture, we'll have images here. Okay, so we'll have images, then user interface through PC or something, we'll be doing some analysis. So first part is segmentation technique. Hope you all aware of different segmentation technique, region based and then contour based, edge based segmentation technique. And after particular region of interest have been segmented, we need to concentrate on the feature extraction. Okay, so feature extraction, this is much important, but nowadays we are not giving much importance to this features, which features are important for your specific applications. So I'm taking this part, then we have to go for a classifier. Okay, neural network techniques. Okay, so as if you give this classifier artificial intelligence neural network and all, so this will be after segmentation, you will be extracting the features, then feature extract vectors has to be given to the neural network and it will be automatically classifying after training and testing the period. Okay, so after it is getting trained, if you are giving a new data for validation, it will correctly diagnose the cases. So this is the complete computer aided system. This can be applicable for all kind of imaging analysis, but now we will concentrate mostly on the medical image analysis technique. Okay, so after this feature extraction technique, the important thing is we need to normalize the data. So we know the normalization, why it is important is if I'm extracting 1000 features, these 1000 features will be in having a different ranges, minimum and maximum value. So always it has to be normalized within a certain limit, minimum and maximum value. So for example, if you have a feature vectors, GLCM, if you are extracting, if you have some mean value from 0 to 1000, and then if you have some standard deviation value from we have 0 to 50. So we are making all the ranges into a common range. It may be 0 to 100 or it may be most in standard form, it has to be normalized between 0 to 1. Okay, so then after that feature extraction, then it has to be given to the classifier. So this point is very, very important. The feature vectors given to the classifier neural network. Types of features, if we see, we have different types of features: statistical features, safe features, texture features, and relational features. So if we take the statistical features, histogram related features, so these are the some of the examples. And then shape features are boundary and then Huff transform, region representation, morphological features. And then texture features, you have second order histogram statistics, and then co-occurrence GLCM, gray level co-occurrence matrix features, and length matrix features, and then texture energy measures. Okay, so then you have some wavelet features also. Okay, so second order histogram features and then wavelet features also. Then you have some relational features, logical relational features. So we all know histogram very well. So in the x-axis you will have a gray value, and y-axis you will have a number of pixel values. So for example, if all the pixels have been distributed in the leftmost corner, you can see the image is dark. Okay, so if the image is bright, almost you have all the brighter pixels. If it is at the center, the almost all the pixels of distribute, all the pixel values are in the center, having a center gray values. So if it is uniform distribution, you will get a better contrast. Okay, so this will be giving the information about the pixel distribution. So after taking the histogram, from the histogram value, you have to take the mean, standard deviation, skew, energy, and entropy. Okay, so these are the formulas for the different uh, features: mean value, and then variance value, and then standard deviation value, energy, and what is the entropy of the histogram features, and then maximum and minimum gray values, and what is the skewness value. Next is the shape features. For shape features or example mainly helpful for finding out the shape of the particular cell component. For example, I'll take example of the cell component, cell features. For example, diabetes cases, the cell deformity will be more. So how to measure the cell deformity? Okay, so cell deformity can be measured, for example, using the circularity, compactness, and then elongatedness. Okay, so these are the some basic features, safe features, which can be helpful not only for cell safe features. You can go for the other safe features can be analyzed. So these advanced regions are chain code, boundary contour, and then Fourier descriptor of boundary contour, and then central moments based safe features for segmented region, then morphological safe descriptors. These are some of the example. I'll list out some of the example safe features. For example, this is the cell. Okay, so in the case of the uh, affected cells, it may get elongated or it may get deformed instead of circular shape. So those cases, you can find out the what is the longest axis and then shortest axis, and what is the perimeter, and then elongation ratio is longest axis divided by shortest axis, and then circularity you have formula, then compactness you have a formula. Okay, so but all the features have its own uh, meaning. Okay, without meaning it is very difficult. Okay, so area of the object, it will be giving the relative size. You can compare the size of the cells, and then center of the area. Okay, so this will know well known center, it will be giving the center position of your cell or any object, and then this will be giving axis of least second moment. So this will be giving the angle of the axis related to the vertical axis. And then perimeter will be giving the shape of your object, and then thickness ratio, this will be giving the roundness, how much round your selected region of interest is. And then irregularity ratio is, so this is inverse of the thickness ratio, this will be giving the regularity of an object. And then you have aspect ratio, so this will be giving the this other name is elongation or eccentricity. Okay, so this will show how the object spread in both vertical and horizontal direction. So this will be find out with the help of the aspect ratio. The next is the Euler number. So difference between the objects. Okay, so that can be find out with the help of the Euler number. Then projection. So this is related to information related to objects shape. Okay, and then some example. Okay, so axis of second moment. So for example, I say no, this will be assuming the center as the center, that the origin is as the center of the area. Then this will be providing the information about the how far from the center the object is oriented, how much orientation, how much angle. Okay, so see here, this is they have drawn a horizontal and vertical normal, and you can see this theta. This will be given the angle of the orientation of the particular region of interest. Then next is the Euler number. Okay, so this Euler number is used for a optical character recognition. So this will be helpful for the character recognition. So this you have to measure how many number of, okay. So for example, this image, if you take, it has 8 objects. 1, 2, 3. You can include separated things also. It has 8 objects and it has only one hole. Okay, so you have to subtract. Euler number is number of objects minus whole. Okay, so this will be having the Euler number. So for each and every letter, you have to identify what is the Euler number and you can find out. Okay, so other way of finding out the Euler number is how many number of convexities and how many number of concavities are there, you have to calculate, then you have to subtract it. Okay, so this has to be done with the help of the finding out these patterns. So we know the images in the form of matrix. Okay, so we need to find out whether this pattern is there for convexity and whether this pattern is there for concavity. Then you have to subtract the number of convexities minus number of concavities. That will give you your Euler number. Then next is you have the other advanced descriptors are chain code for boundary contour, and then Fourier descriptor, and then central moments, then morphological shape descriptors. So these are all shape descriptors. Then next is the second order histogram statistics. Okay, so we have discussed first order histogram statistics. Histogram statistics, the probability of occurrence of pair of gray levels. So if you take the first order histogram statistics, it gives the distribution of a pixels by considering each pixel individually. So instead of the second order histogram statistics, we will be giving the information about a pair of occurrence of pair of gray levels, the relation between the pair of gray levels. Okay, so that is the difference between first order and second order histogram statistics. So if you see here, Q is one pixel and R is another pixel. So same like that first order histogram, you can calculate the entropy, angular moment, and contrast, and then inverse difference moment, and then correlation, and also you have mean, deviation, entropy, angular second moment, mean. Okay, so these are all second order statistical features. Then next is higher level features or texture features. That's all. That's all about statistical features. Then next is texture features. Okay, so texture means that in of the surface, okay, surface of the image, how the intensity variation is there. So first type of texture features are gray level co-occurrence matrix features. Okay, so this is nothing but you have to, this will be generating a matrix, GLCM matrix, which give information about how often a pixel with gray value occurs horizontally and in different directions. Okay, so along horizontal direction, along vertical direction, along right diagonal, along left diagonal. Okay, so horizontal, vertical, and then right diagonal and the left diagonal. Okay, so this will be giving the occurrence information about how often a particular pixel with a particular gray value occurs in different directions. Okay, so this, if you see here, so this is an image matrix. So this will be calculating first what is the GLCM matrix. For example, 0, 0. So how many combinations of 0, 0 is there along horizontal, vertical, and then diagonal, and then right diagonal and left diagonal. Okay, then it will be calculating combination of pixels with 0, 1, 0, 2, etc. Okay, so first it will be it will be getting the co-occurrence matrix. Okay, so from the image you have to first form the co-occurrence matrix. Then from this co-occurrence matrix we have to find out the second order features. Okay, so you can get basically 11 numerical features. Okay, so angular second moment, contrast features, entropy, variance, correlation, inverse difference moment, and then some average features, some variance features, some entropy, information measure of correlation feature 1 and 2. Okay, so for example, if you have an input image, then you can frame the co-occurrence matrix along different direction. For example, 0 degree, this is along horizontal direction and you can get 11 features. And if you take the along 45 degree, again you will get again another set of 11 features. Then along vertical direction, another 11 features you'll get. And then along the left diagonal, you will get another 11 set of features. So totally you will be getting around 44 features. Okay, 44 features you'll get from the GLCM features. Okay, and then this also a certain meaning for each features have its meaning. For example, contrast have discriminating ability, and then entropy has a strong discriminating ability. Variance also is having a discriminating ability. Correlation have discriminating ability, and then some average. So this will be giving the how much similar the gray level pixels are. Okay, and this is also information measure is also same as sum of average, and this is also same. Okay, so like that each have its own meaning of features. Okay, so then angular second moment or energy, so this doesn't have a distinguishing ability, but this will be giving angular information, orientation information, and this is inverse different moment also doesn't have any information. Okay, and then concurrence matrix, Horlick the scientist, he found he has written a coding for MATLAB programming to find out these 13 Horlick features, and these are the all 13 Horlick features. Okay, autocorrelation, contrast, correlation, all these features, cluster shade, dissimilarity, energy, entropy, homogeneity, and then maximum probability. Okay, so for example, I'll take autocorrelation. Okay, so autocorrelation, this will be giving the information about linear spatial relations. Okay, I'll tell it in better way. For example, dissimilarity will be giving the variation of gray level pairs. Energy will be giving the uniformity, how the textures are uniform. Texture informations are uniform. This will be giving the uniformity about the information. Then entropy will be giving the randomness of energy distribution. Okay? So each features have its own mathematical formulas to calculate parameters, and it has some physical meaning of. Then for example, you can implement this for 13 direction for a 3D images. Okay, so for example 3D images you can do for a 13 directions. Okay, so 13 directions, so 13 directions different distances. Okay, so you can go for a distance, you can take the neighborhood pixels 1 distance with 2 distance, 4 distance, up to 8 pixels distance. Okay, so for example 13 features I am extracting, 4 different direction I am extracting, and then 13 different features I am extracting. Totally I can get a 676 features for a single image from the GLCM alone. Okay, remember that. And then run length matrix. So this is also like a GLCM matrix, run length matrix features. So this will be giving information about a set of consecutive collinear pixels having the same grade level. Okay, so this will be taking row by row each run. Okay, so the run is nothing but the number of pixels having the same intensity in a particular direction. You can take in a horizontal direction or you can take in a vertical direction. Like GLC, here are matrix, you have a different features. These features, short run emphasis, long emphasis, gray level uniformity. So these are the some of the features. Okay. Here also you can have some physical meaning. Okay. So meaning for, so for example, uh, for example, see here, short passes. So if this value is higher means greater means, then it you can conclude each has a more fine textural information. Okay? And long run emphasis, if it is greater means it has a more core structural information. Okay, and then GLN, gray level non-uniformity, means similarity. So this will be giving the information about the similarity of the pixels. Okay, so like each and everything will have a certain meaning. Okay, so that is important. For example, why I am insisting this again and again is, for certain applications you have to go for a shape features, that is important. So you need not bother about this texture features, but certain applications you have to go for a you have to analyze the texture features, need not require the shape features. Okay, so that is important. Okay, you should understand first what type of features is important for your specific medical image analysis, then you have to choose that particular features. Okay, so these are all run length features. So as I here, see here also you can extract it. See, 676 features can be extracted from the GLC matrix. So you can extract those many. For example, you have 11 features, so you can extract 4 into uh, 13 directions. You can get that those many features you can extract from the run length matrix features. Okay. Then next, loss texture energy features. Loss texture energy is nothing but we have studied certain mask edges in the Sobel edge direction, and then Gaussian, and then Laplacian of Gaussian. We know we have a mask. Okay, so these are the mask. Okay, so this is called as a level mask. Okay, so this is level mask. This is nothing but a Gaussian mask. So this is nothing but a weighted averaging mask. And then if I was gradient, this will be response to the edges. And then Laplacian of Gaussian, this is combination of Laplacian filter and Gaussian, and this will be detecting spot, okay, dots present in the particular image. For example, calcification. Okay, so for if I am interested to find out the calcification, you have to go for this particular type of feature. Okay, then you have a Gabor detector. This will be detecting the ripple information. So you have a different mask. Okay, so this mask can be multiplied. Okay, so for example, so this is one mask, this is multiplied with another mask. So E5 and L5 we are multiplying and we are getting one two-dimensional matrix. So this can be applied as a mask and it can be used for extraction. Okay, so from this also you can get a 9 feature vectors. Okay, by combining different combination of this mask, multiplying and then after that dividing. Okay, so here if you see here L5 is multiplied with E5, E5 is multiplied by L5, then I am dividing it with this, finding the ratio. Okay, so like this 9 different feature vectors can be found. Okay, so these are the multiplication: level multiplied with level, level multiplied with edge, level multiplied with the ripple, level multiplied with the spot, and then edge. Different combination of mask will be giving a different information. Okay, so this is the process happening. So this is your input image, and these are the different mask. Okay, so different combinations of mask I explained as previously. So these are the filters. Then this is filtered images. Then this is energy map. We have to extract energy from this. Then I am doing a normalized value. Then from that I am extracting the feature images. Okay, so this is law energy measures. This is also coming under the texture type of features. Okay, then wavelet features is also coming under the texture type of features. Okay, so wavelength features is nothing but we know wavelet transform, Fourier transform. We need to apply a wavelet transform, and then this will be giving a two different types of coefficients: detail coefficients and this is approximation coefficients. Okay, so approximation coefficients will be giving only the edge information. Detail coefficients will be giving information about the texture. Okay, surface information. Okay, so for my application I need only the contour information, then I can make it 0 this detail coefficients. I can go for this only this approximation coefficient, and this features can be used for further classify. Okay, so for simply if we take a 2D discrete wavelet transform, first level of wavelet transform, this first window, this will be dividing into low high, high high, low low and high low. What is the meaning of it? It will be dividing into 4 frequency component. Okay, so low means low frequency component, high frequency component. So this will have, this component will have low and high frequency information. This will have high and low frequency information. This will have both low information. This is low frequency information. This is having a high frequency information. We know high frequency informations are nothing but edges. Okay. So if I'm taking the dot, okay, and I'm doing first level of wavelet transform, first degree of wavelet transform. So this will be having a edge information. This will be having the texture information. Okay. So this will have a combination of this. Diagonal coefficient will have a combination of this. So this is first level. Then if you go for a second level of wavelet transform and third degree of wavelet transform. So if you see here third level of wavelet transform, if you see high frequency component, this will have a clear edge information. Okay. So if I'm interested only this edge information, you can take this quadrant alone, you can use for a classifier. And this will have low frequency information, will have a surface features information. Okay. So this is nothing but how to carry out this. You have to decompose, downsample the columns, okay, decompose, and then row wise you have to do. Then you have to convolve with the filter, okay. Then you will be getting the, see here, this is down row wise you have to downsampling it, and then column wise you are downsampling it. So you'll be getting low and high frequency detail components, and here also low detail components, high frequency detail components, and then low and high. And after that you are downsampling second order, so you'll be getting a approximation coefficient and then detail coefficients. Detail coefficients, horizontal, vertical, and diagonal. You have some approximation coefficient is this only. Okay, only one approximation coefficient, but this also low detail coefficient. This is detail coefficient. Low also detail coefficients. Okay, so then this coefficients can be taken as a feature vectors. Okay, so this is wavelet features. It's taking. So this is one example, one Lena image, and you can see here having, if you see here, this have a high, this has only the edge information. Okay, so this is first level of decomposition, second level of decomposition, then third level of decomposition. So for example, see, you have a toolkit for in MATLAB, okay, for this to carry out. So this original image, okay, so this is first level decomposition, second level, and third level of decomposition. So first level decomposition, you can see here, these are the detail coefficients. Okay, horizontal detail, vertical detail, and then diagonal details. Okay, second level and third level. You can see if here we have only this detail coefficients, and finally this is approximation, that is edge information, and this you can you have a different types of wavelet transformers out there. They have applied a Haar transform here, and you can change the transform and you can get a n number of features. Okay, and you see here, so this is original image. You have to go for a discrete wavelet transform. So this is the decomposition of first level, and if you do inverse, then you will be getting a synthesized image, and this is detail coefficient alone have been extracted. Okay, so whatever coefficients you need, that alone can be extracted, and that features alone can be given to the features. Then advanced wavelet transform is duality complex wavelet transform. See here, this is doing only in one direction only, 45 degree only. But this dual tree wavelet transform, complex wavelet transform, this will be working in 3 different directions, 6 different directions. Along 45 degree, 75 degree, 15 degree plus as well as minus direction, minus 45, minus 75, and minus 15 degree direction. Okay, so this is advanced dual tree complex. Then you have a different edge features are there. You can ask, we have Sobel operator, Canny, Roberts operator. Then what is the need for going for this? Again, the features. So these are all basic edge operators. But what is the need for the other edge features? Okay, so you need multi-resolution, localization, critical sampling, directionality, anisotrope. First 3 things, the parameters can be achieved by this basic operators, edge operators. But this directionality and anisotropy cannot be achieved by these things. So that's why we are going for the wavelet transform and then wavelets and edges. Okay. Then advanced techniques are uh, uh, advanced wavelet coefficients. You have, apart from wavelet transform, you have a ridgelet transform, curvelet transform, contourlet transform, bandlet transforms. These are the different transforms. See here, we have seen here this dual tree complex wavelet transform will be working under 6 different directions. Only 6 directions. But if you see this combination, ridgelets and curvelet and all, in all direction, it can work out, it can find out exact edges. Okay. So that is why we have to go for a other kind of wavelet transform. Okay. So, for example, edge detection, for example, if you take a wavelet transform, it can detect only horizontal, vertical, and 45-degree orientation only. But contourlet we can do in any direction, any orientation. Okay, and this will filter the noise also. Okay, so this can be implemented by a combination of filters. N series of filters has to be together. It has to be worked. Okay, so this is carried out in 2 stages: subband decomposition and then directional decomposition. Okay, subband decomposition is downsampling. I said no. It has to be decomposed into different frequency level. So this is decomposed first into Laplacian pyramid, and then second level of decomposition you are using a series of directional filter bands that is applied. Okay, so this is a band decomposition. This is second level of second stage. Okay, and then decomposition, I said no, you have to go for a Laplacian pyramid, and then second is directional filter bank you have to apply. Okay, so for example, so you have an image, low pass band subband filter, that is first stage. Then second stage is band pass directional subbands. So this will be diagonal alone, and this, if you see here, this is taking a n number of directions, and if you see here, this is taking almost different, whatever angle you are giving, this will be giving a multi-scale decomposition, and different direction it will be finding out the edges. So this is contour line. So if you see where, you can ask where it can be applicable. Okay, apply. So this is biometrics analysis, we know. Okay, so this contours, we need to identify, we should not miss out any of the edges. Okay, so this is this, for example, this reference point, they have taken a particular region of interest, and it has been divided into contourlet, and it has been divided into different decomposed images, decomposed into different levels. This is the output of contourlet transform. Okay, so then from this you can identify minimum, that is D value and then F value, different features. You can extract, you have a formula to extract the features from that contourlet transform. Then other application is biometrics application. You can see here the contourlet transform, the facial image, and then Laplacian pyramid they have applied, then directional filter bands applied, and they are extracting into a different levels, level 1, 2, 3, 4, and from this you can get the different features. Okay, then next is curvelet. Okay, so curvelet is, this will be partitions the curve into collection of ridge fragments. Okay, so ridge fragment, and then uses a ridgelet transform. See here, I put here in the image. So you can see here, this will be segmenting into different ridges first. Okay, so separated into different ridges, then you have to apply a ridgelet transform. Clear? So now if you see here, curvelet transform, so these have a different steps. You have first subband decomposition, then smooth partitioning, then normalization, then you have to analyze ridgelet analysis, and after this you have to extract the features, mean statistical features from the from after applying the curvelet transform. Okay, then subband decomposition, this will be 4 stages of curvelet transform. First thing is subband decomposition. So it will be first decomposed into different frequencies level, then smoothening, and then renormalization, then Dirichlet analysis. For example, so see here, this is original image, subband decomposition, smooth partitioning, and then so this has to be applied for the Dirichlet analysis. Okay, so you have to take block by block, and then FFT, then inverse FFT, then Radon transform, then you have to go for a Dirichlet transform. But this is very, very complicated. The curvelet transform is very, very complicated. But now you have a built-in function. Only if you are interested in application point of view, you can go ahead and then you can work out along with some mathematical professors. Okay. So for example, so these are the some different subbands. Subband 1, subband 2, subband 3. Then they are partitioning into a different ridges. Okay. Then after that, Dirichlet transform is applied, and then you have to get the Dirichlet coefficients. Then this features has to be used for a feature classifier. Okay, so this is one of the curvelet examples. Okay, so this is liver segmentation purpose. You see here, this is abdominal CT image. Okay, so abdominal CT image, this is your histogram. So this part is having a liver. Okay, so using that histogram, they have identified the liver, and then see here, they have applied the segmented. They have segmented the liver part alone. See here, segmented the liver alone. Then they have segmented the tumor part alone. Then after this, from the segmented part, they have applied the curvelet coefficients extracted, and for automatic classification into different stages or diagnosis for evaluation of this tumor region. Okay. The next advanced thing is Gober filter. So this is nothing but sinusoidal plus Gaussian combined, which we give a Gober filter. Okay. So this is the Gober wavelet equation. Okay. So this is 2D Gober filter equation. So from this, you have to extract the odd and even component of this signal. Okay. So now I'll go directly thing. So this Gober transformation, you can go for a different orientation, different subbands level, okay, frequency, okay, and then you can find out the standard deviation of Gaussian distribution. Okay, so Gober transform, you can vary the sigma value, and you can get a different filters. I'll go directly to the applications. Okay, so see here. So this is first level, second level, third level, and fourth level. This is reconstructed. Then from this, you have to get the and extract the features after Gober filter. Okay. So these are Gober filter, and you can get the real and imaginary part of your magnitude value and the real and imaginary part of your Fourier domain value. Okay. So this also you can go for a different orientation. 0 degree, 90 degree, and then 30 degree. So this is your raw image. So 0 degree, 90 degree after applying the filter sets, then 30 degree. Okay. So here also you can vary the parameters theta along a different direction. See here, they have applied at 1, 2, 3, 4, 7 different angles. Okay. So 7 different angles. You can go for a n number of angles, and then n number of frequency subbands, and then you can vary the sigma x and sigma y of your Gaussian distribution, and you can go for a n number of features. Okay, so this is Gober phased, again applied to the fingerprint for biometrics application, for biometrics applications. So see here, in biometrics you have a different, see here, this biometrics have some curves. But what we are doing analysis. Okay, minuc. Okay, minuc is nothing but this curves. Okay, so minuc, that is one thing, and then you have a different pattern, core point, delta, line types, ridges, and then ridge patterns. These are the different fingerprint features. Okay, so for example, this is if two crossover, this point is called as a crossover. So this point is called as core, And if it is bifurcate, this point is called as bifurcation, and this point is ridge. And you can see here, this is separate area, this is called as island. If you see here, some triangle shape, delta shape is there, so this is delta, and then pore. So these features can be analyzed. Okay, so core, delta, so this is core, and then this is core. Okay, so this applications, you can go for this curvelet, contourlet, and then different Gobar filter, you can go for a biometrics analysis. Okay, so we know different scanning, optical method of scanning, thermal, and then capacitance method, ultrasound scanning method. Okay, so we know here optical, nowadays all places we are using optical coder. So code, minutia, valley, and then risk, these are helpful for so you will have a template for already captured biometrics. You will have a template. For example, if my biometrics is there, no, that will be stored in the database. Then each and every day when I come for biometrics, so this will matches with the existing template, and it will identify the person. Okay, so this is the miniature matching. Okay, so this is already template. Then whenever you come daily, then this will be uh, match with the already template, and it will identify the person. Okay, so you will have a database of all the templates. Okay, so you will have all the, for example, they have taken a minutia as one feature, then it will be matching and then validate whether it is the particular person or not. Okay, so biometric capturing, image, and then image processing, that is saved as a template, and then it has to be matched with the stored data, then it will be identified. So if it achieves 95% matching, then it will identify the particular person. Then iris scan, also nowadays they are using for biometrics application, iris scan image, localization, then feature extraction, then compare it. Okay, and apart from that, next point is feature selection. Okay, so we have discussed so far different features. Okay, so imagine for particular applications, if I am extracting, see, 50% of the feature extraction techniques only I have taken. So if I am extracting almost all the features, I may get 1,000 features. Okay, so you have to, for a particular application, you cannot go only for that particular feature. You can go for a n number of features, then go for a feature selection technique, which is highly discriminating the uh, uh, objects for a particular applications. Then you have to go for a feature reductions. For example, I have 2,000 features, so among that I can take a 15 features alone, which is highly significantly distinguishing my diagnosis purpose. Then you have that those features alone has to be given to the, I'll skip on all these things, feature reduction and feature selection. Then after this has to be ranked different features, and then first 15 features which is highly significant has to be uh, given to the classifier, then you will get a better accuracy. Okay, so that is very important. Okay, so this feature extraction technique nowadays have been used in different area, for not only for medical applications, food processing, biometric analysis, medical image analysis, and then satellite global information system, land, and then satellite analysis, it has been used. Okay, so I have concentrated now the feature extraction technique. I just want to share one more thing. Okay, so I think now it is an advanced, now we are in advanced thing. Okay, so we have extracted the features, and then we are diagnosis that. Okay, so this is one of the paper published by one of my research scholar, that is this will be counting the lymphocytes. Okay, so lymphocytes, so we have implemented this using a deep learning. Now deep learning architecture is there. So what is the advantage of this deep learning network is no need for segmentation. Okay, you can directly train it and you can give it. Okay, so here this paper, we have used the uh, technique to uh, to identify to label the lymphocytes. Okay, so see here they have taken the histopathology images, immunohistochemistry of the slides of the images, and then we have taken a region of interest. Then we need to increase the number of images, so we have done some augmentation technique, and we have used GISNet or ResNet, VGG deep learning net, and then inception net, inception v2. Okay, so what we have done here is we have identified the lymphocytes. Here, this is your original image. So this is colon cancer, breast cancer, and prostate cancer. Okay, so these are the original image. So see here, this will be identifying, labeling the lymphocytes, and this technique will be giving the automatically will be giving the counting of the lymphocytes. Okay, so it is very difficult. If you go to the histopathologist, they need to manually count over a particular region of interest mm square how much lymphocytes are there. But this will do automatically. Okay, so now we have implemented this for a lymphocyte count lead down. Okay, so this is some advanced technique now. Deep learning techniques or advanced technique. So why I am going for this advanced techniques? No, so here no need to base your time, much of time, in your segmentation technique. Okay, so no need for segmentation. So automatically you can go for achieve the feature extraction between the normal and the different stages of cancer, or whatever the diseases may be. Different stages of diseases can be taken, and automatically you can extract the features, and it can be given to the classifier, and it will give the output. Okay, so I think hope I have covered much within this time given, uh, 1 hour. This much only I can cover. You can approach me at any and me for any no, doubts and all. Uh, I'll
All
stop
right, ma'am.
with that. Yes, if you have
Yes,
any
ma'am.
queries, you can ask.
All right, ma'am. Thank you so much, ma'am, for your valuable time and sharing all the information about the medical imaging analysis, and like how wonderfully you have related the image with the biometric and the iris, and so you have related with the new histopathological analysis of your paper. So it was quite wonderful listening from you. Thank you so much, ma'am.
Thank you, Anupam. Thank you, Mr. Anand.
Thank you.
Thank you.
Thank you. You can leave. Leave.
Yes.